Okay, so this is the video lesson for day 1 of derivatives. Let's first recall how we do linear functions and their slope. Now a linear function, has the same slope at all of its points, and this is the slope. And if you remember, the most basic definition of slope is change in y, which we denote with delta y, over change in x, which is delta x. Okay, a parabola, though, will have different slopes. Right? And any other type of function is going to have different slopes at different points. And so we have this idea of a tangent line. Okay, so let me go ahead and draw just a basic parabola. All right, the parent function, so to speak. So let's say we have a parabola and its vertex is at 0, 0, and if you just kind of zoom in at any one point of this parabola, it kind of looks like a segment of a line, and that's how we're going to think of it. Okay, so we're going to think about tangent lines. The slope of the tangent line is the same as the slope of the function at that point of tangency. All right, so let's put our first point right here. All right, now if I do a tangent line, now remember, tangent line is a line that just touches the curve in one place. You learned this in geometry when you did circles and lines that are tangent to circles. But really, tangent lines can be anywhere on any curve, but they only touch once. So if you had to estimate the slope of this line, I would say it's negative in some pretty large number, like maybe -4. Okay, as opposed to right here, at the vertex, well, if this is the true parent function, that tangent line is going to look like this, and this slope is going to be a 0 slope. So the slope is going from negative to 0, and then right here it's positive. So if I put the tangent line right here, all right, we can see that this line right here has a slope of probably about +1, maybe a little bit more than that, but a positive number. And if we were to continue on in this parabola, the number would get larger and larger and larger. Okay, so that's what a tangent line is, and we're going to use that on the next part. It says to find the slope of the tangent line, you approximate the slope of the secant line by choosing points closer and closer to the point of tangency. So we're not able to find the slope at one line, but what we are able to do is to take 2 points and to approximate the slope of this curve, okay, we're going to find the slope of this line right here. Now this line is not tangent. If you can see that it's crossing in 2 different places, this is what we call a secant line. Secant line crosses in 2 places. Tangent line crosses in once. But if you're just wanting to get an approximation, and that's the key word here, if you're just approximating, well then they are basically the same. They're very close to each other. And as this little segment right here gets smaller, as these 2 points get closer and closer to each other, the secant line is going to become the tangent line. And if you could say that these 2 points are infinitely close, all right, they're infinitely close to each other, meaning the space between them is infinitely small, then the secant line actually does become the tangent line. All right, so this is where we get a lot of this information that we've seen many, many times. Okay, so what I'm going to do is I'm going to show this to you in something you're used to. Okay, so what we're going to say here is we're going to let x be the point of tangency. Okay, so that's x right here. So this point is going to be x, comma, f of x, because the curve here is f of x. If we didn't label it, let's label it now, f of x right there. Okay, and that's what that y value is. That y value is f of x. Okay, for this particular x. All right, well then this value right here would be x plus delta x, whatever we're changing in x. Don't let the notation throw you off here. All I'm doing is saying I'm going to add this value to this value, the next value, to get the total. So that's what the x value is at this point. So the x value at this point is x, I did not mean to write the comma just yet, x plus delta x comma, and then what would the y value right there will be? Well, it would be f of whatever the x value. So in this case, the y value is f of x plus delta x. Well, that's now the y value. You may think, well, this is all a waste of time. Okay, well now let's think about how we would find the slope here. All right, the slope we know would be change in y over change in x, because it's a line. We're talking about the secant line here. So let's expand this just a little bit. Let's do y2 minus y1, thinking back to slope formula from Algebra 1, f of x plus delta x minus f of x all over x2 minus x1, so that would be x plus delta x minus x. Well, you notice something in the denominator happens. The denominator narrows down to just delta x. Okay, so we have f of x plus delta x minus f of x over delta x. And we didn't use delta x in the past. What we used instead was h, okay? And what I'm going to do is I'm going to take limit of this. In order for this secant line to become a tangent line, really I'm going to switch to a third color here. In order for this to become tangent, what do we want to happen to this right here? We want it to get smaller and smaller and smaller. So we want the limit as delta x approaches 0 of this whole thing. This right here, I know it seems kind of weird and messy, but this should kind of look familiar. All right, I'm going to rewrite this in terms that you're a little bit more used to. The limit as h approaches 0 of f of x plus h minus f of x all over h. And you're probably even more used to, instead of the x's, to have an a there. This is this thing you've been practicing now for a couple of years. And this is how you're going to find something called the derivative. So the slope of the tangent line, all right, changing the secant to the tangent. Secant is something we can do algebraically. In order to find the tangent, though, we have to add limit in front of it. That is what the derivative is. Okay, the derivative of f of x is denoted by f, and it looks like a little apostrophe there. This is called f prime of x. Prime. That's what that means. That's the derivative. Okay, so let's actually take the derivative. We just have a couple of examples. So the first one says for each function find f prime of x. This means find the derivative. Okay, so let's do that in part A. We are going to take the limit, and I'm going to go ahead and use h here. As h approaches 0, and it's going to be of f of x plus h minus f of x all over h. This is what we're going to do each time. Okay, so limit as h approaches 0, and then f of x plus h, we plug in x plus h in for x. So x plus h squared plus 1 minus parentheses x squared plus 1 all over h. Okay, so now we need to clean it up, because if I were to take the limit right now by plugging in a 0 in for h, I would get 0 over 0. So this means that the limit exists, but I need to do a little bit of work. So I need to multiply x plus h times x plus h. So that's going to give me x squared plus xh plus xh when I multiply all that out. So 2xh or 2hx, it doesn't really matter, plus h squared plus 1 minus x squared minus 1, and again over h. So notice now that we have some things canceling. The x squareds cancel, the -1 cancels with the +1, and what you have left you can factor so that you can simplify. So the limit as h approaches 0, and then we have h, and in parentheses 2x plus h over h. The h's now cancel, and now we can do the substitution. Okay, so now if I substitute 0 in for h, I am left with 2x. Okay, this is the answer to the first question. What is the derivative? What is f prime of x? It's 2x. What does this mean? This function right here, it's a whole new function. This is describing the tangent line at any given x. So what we're going to look for in part B is finding the slope of f of x at the specified x value. Okay, so to answer part B, we're going to take our derivative and we're going to plug in our x value. Okay, so we have, I'm going to write it all out here. We have 2x and we have x equals -1. Let's combine these two. This would be 2 times -1, which is just -2. That is the derivative of the tangent line at x equals -1. So if I were to draw this parabola, locate x equals -1, draw the tangent line, the slope of that tangent line would be -2. So now we get to part C, which is going to ask us to write the equation of that tangent line. Okay, well we have the slope. I want you to draw an arrow here. This is the slope. What else do you need to write an equation of a line? You need a point. Okay, well we already have the x value of the point. Okay, the x value of the point is -1. What is the y value? Okay, don't go to your derivative function. Go to your original function to do this. The y value is just going to be f of -1, not f prime of -1. That's for the slope. But go back to your original function. So f of -1 would be -1 squared plus 1, which is 2. So now my point is -1 comma 2. So if you remember, y minus y1 equals m, parentheses, x minus x1, we're going to plug that in to find the equation of the line. So I have y minus 2 equals -2, x minus -1, or we could say x plus 1. And the best part about calculus is you get to leave your line that way. You don't have to simplify it. Okay, let's try another one. Okay, example 2. Just a little bit more complicated of a parabola, but all the same steps. Okay, first thing, A, we need to find the derivative of f prime of x. And the way we're going to do that, remember, is to take the limit as h approaches 0 of f of x plus h, which is going to be 3x plus h squared minus 4 parentheses x plus h plus 1. So that's f of x plus h. Then we're going to subtract just f of x. And I'm using parentheses so that I make sure I subtract everything. And all of that over h. This is what you do every time. Now, if I were to do a direct substitution right now, I would get 0 over 0. Okay, so what I want to do instead is to work a little bit, simplify, factor, remove the discontinuity so that I can find this limit. All right, now if you have questions over this algebra, you need to ask me in class or you need to come in for tutoring so that I can help you. This is all stuff you should be able to do by now, so I'm not going to spend a lot of time in this lesson explaining that. But you might have some questions, and always feel free to ask. Okay. Now, if you look, a lot of things are going to cancel. Minus 1 cancels with plus 1. 4x cancels with negative 4x. Negative 3x squared cancels with positive 3x squared. Okay, so in the next one I have the limit as h approaches 0. And I have 3 terms left. They all have an h, which is good, so that I can factor that out and cancel with the denominator. Alright, once you cancel out this h over h, you're able to do the direct substitution. And so we get 6x minus 4. This is the derivative. This is f prime of x. It also stands for the slope. So if I want to find the slope of the tangent line at x equals 2, okay, I need to plug in 2 in for x into my derivative function. So that gives me 12 minus 4, which is 8. Okay, so this is the specific slope at this x value. So now when I get to part C, let's write down what we have. We have that the slope is 8, and the point, well, we have the x value. They give it to us at the very beginning. To find the y value, remember you go to your original function and you find f of 2. In fact, if you knew you were doing this, you could go and do this at the very beginning. And when you plug 2 in to that function, you're going to get 5. And so 2, 5. And so now you write your equation. Y minus 5 equals 8, x minus 2. And you do not have to simplify that. Okay, bring your questions to class.